Hello, and welcome to question 4, Asymptotics Potpurri. Okay, so this question says, give a tight runtime bound for mystery as a function of n, the length of the input array. Okay, so before I even walk through this question, I want to give a brief overview of how I approach asymptotics questions. I'll first look at the runtime of the operation, and then I'll multiply it by how many times that operation is actually executed for. So how many times operation gets executed? And this kind of, general structure is really essential into understanding and to figuring out what the asymptotics runtimes are for any given asymptotics question. Okay, looking at this 4.1 question, they give you this public static int mystery function that gets an array as an input and also returns an array as an output. And then it has a while loop while this Boolean value is equal to true. And then while it's equal to true, then perform all these operations. And it has a for loop that loops through all the values in the array. And then it checks to see if the previous value is greater than the current value. If it is, then swap those two values and then make this Boolean temporary Boolean value equal to false. And then it swaps these values every single time we iterate through all the values in the array. So this example right here is an example of what bubble sort would do. And knowing this is out of scope for right now. Uh, but essentially what this function is doing is it's comparing all the previous values to the current value in the array and then swapping those two values if the previous value is more than the current value in the array. Okay, so I mean that this runtime is gonna have a worst case and best case scenario. The best case scenario is that the algorithm terminates without swapping any elements. And that essentially means that the inputted array is already in sorted order. So the best case scenario is that the input array is already in sorted order. Okay. Then the worst case array is that the given array is in reverse sorted order. So you have to go through every single element and compare each of the values and then compare and then swap those values. So in this case, the worst case is that the input array is in reverse sorted order. Okay, awesome. But now how do we write this in terms of asymptotic notation? Well, if you want to translate this from English into asymptotics, the best case scenario is just going to return all the values in the array because we're going to still loop through all the values in the array, but not actually go through this inner if statement loop of checking to see if any value is greater than its consecutive value. So in that case scenario, the best case scenario is going to have a runtime of omega of n. But then for the worst case scenario runtime, we're going to loop through all the values in the array and then once again also compare and swap each consecutive value. So in that case, the runtime for the worst case scenario is going to be omega of n squared. Oh, that's an n. Omega of n squared. And therefore, the overall runtime of this question is going to be and then big O of n squared as such. Okay, moving on to 4.2. Question 4.2 says to give the tight asymptotic bound for pink trout. Okay, looking at this question just briefly, we're given some kind of recursive call to pink trout where A is being decremented by 1 each time. And then the base case is going to return a 1 when A mod 7 is equal to 0. Okay. So right here, we know that this given base case is going to have a runtime output or asymptotic runtime of omega of 1 because we're going to return 1 if a mod 7 is equal to 0. Okay, awesome. Then, if not, we're going to recursively call pink trout by decrementing a minus 1 by 1, and also incrementing this overall value of pink trout by a value of 1. But intuitively, we're going to always reach a value equal to mod 7 by decrementing a certain number of values. What I mean by that is, for example, if we have an input A value, let's just say it's 12, we're going to eventually reach an input value for pink trout that's going to be equal to 0 if you do mod 7. And once again, mod 7 returns the remainder of the number divided by 7. So for example, 12 mod 7, so in this case, running pink trout of 12 minus 1 would return, a mod 7 would return a value not equal to 0. And thus you would then call this on a of 11, which would return pink trout of 10, and then we call this again a is equal to 10, which is going to call pink trout of 9, and then we call this again a is equal to 9, 9 minus 1 is equal to 8, so we call this one more time when a is equal to 8. And in this case, if we call pink trout of 8, it calls the function of pink trout and a becomes 7, but 7 mod 7 is equal to 0, so it's going to return a value of 1. So we eventually reach a case that's going to return our base case value of 1. And so therefore, this runtime is also constant because any single input value is going to reach a constant runtime notation. So that's why pink trout's runtime is omega of 1. Okay, awesome. Then for this last question, it says, give the runtime bound for this last mystery function. Okay. This mystery function, just looking at it from the get-go, it takes the input value of n, and we have a base case of n is equal to 0, then return 0. And then this return recursive call does look pretty meaty and pretty scary, but actually if you break this down, it actually is pretty intuitive. So what this call is essentially saying is it's basically calling mystery of n, and then for every mystery of n call, it's breaking apart that n call into 3 n divided by 3 addition calls. And what I mean by that is, for example, if we were to call this function mystery of n, okay? If n is a number greater than 0, then we're going to call mystery, I'm gonna abbreviate mystery as m just for simplicity purposes. If we call mystery of n, we're going to call m of n divided by 3. And then we're going to call it, once again, m of n divided by 3, and so on and so forth, until we've reached a value that is close to n is equal to 0. And this is the same thing as to the previous calls. As we go up a level, we're always going to add one more call to each given call in the code. So that means that this top mystery line over here is going to have 3 recursive calls of m of n divided by 3 and m of n divided by 3, and you're going to add all of these calls together. And therefore, each individual call within this level, for example, is going to have 3 calls, and then same as this, and same as this, and so on and so forth until we've reached an n value equal to 0. And so if we view this in terms of like the number of total calls per level, we can see that in the first level, for example, level, I'm going to abbreviate, actually I'll put a variable that's more intuitive. I'll say L, if L is equal to 0, we can see that there's only one recursive call. In other words, if you say that 3 to the power of 0, we have one recursive call. Then for level 1, we see that we have a total of 3 recursive calls, or in other words, we have 3 to the power of 1 recursive call, or 3. And then level 2 and so on and so forth follows the exact same pattern, where in level 2, we have 3 to the power of 2 recursive calls, or 9 recursive calls. And this structure, this tree-like structure is going to follow this pattern where we're going to we're going to see a pattern of 1 plus 3 plus 9 plus all the way until we reach this value of 3 to the power of log base 3 of n. And the reason why I'm doing 3 to the power of log base 3 of n is because we're splitting up each recursive call into 3 other recursive calls. By doing this, we eventually reach a log base 3 of n runtime. But in a different example, if there was only a branching factor, or if they only had 2 factors coming out of each recursive call, that will be a log base 2 of n branching factor. So that means that this summation is going to simplify to 1 plus 3 plus 9 plus n. And therefore, this overall runtime is just going to be omega of n. And that's your solution to this question, and then the end of question 4.